Section 15.5. The pendulum. In this session, we will explore different types of pendulums and the physics that governs their periodic motion. We will begin with the simple pendulum, investigating the specific conditions required for it to follow simple harmonic motion, such as the small angle approximation. We will then derive the formulas for its period and angular frequency. Moving beyond point masses, we will examine the physical pendulum, which involves rigid objects of various shapes. Finally, we will look at the torsional pendulum, where a twisting wire provides the restoring force. By the end of this outline, you will understand how mass, length, and gravity interact to create these rhythmic oscillations. A simple pendulum is a localized model consisting of a particle-like bob with a specific mass, represented by m. This bob is suspended from a fixed point by a light string of length L that does not stretch. When the bob is pulled to the side and released, it oscillates in a vertical plane. This motion is driven by the gravitational force acting downward on the mass. The diagram shows the forces at play. The tension in the string pulls toward the pivot, while gravity is broken into two parts. The radial component of gravity is balanced by tension, but the tangential component, mass times gravity times the sine of the angle theta, acts as a restoring force that always pulls the bob back toward the center. To understand the motion, we apply Newton's second law in the tangential direction. The restoring force is equal to the mass times the tangential acceleration. Because the force acts toward the equilibrium position, we write it as negative mass times gravity times the sine of the theta. Since the arc length s is equal to the length L times the angle theta, the acceleration can be written as the second derivative of theta with respect to time. This leads us to an equation where the second derivative of the angle equals negative gravity divided by length multiplied by the sine of the angle. Crucially, this is not yet the form of simple harmonic motion because the force is proportional to the sine of the angle rather than the angle itself. To simplify the math, we use the small angle approximation. When the angle theta is kept small, specifically less than about 10 degrees or 0.2 radians, the value of the sine of theta is nearly equal to the value of theta itself in radians. By substituting theta for the sine of theta, our equation of motion becomes much simpler. The second derivative of the angle equals negative gravity divided by length times the angle theta. This matches the mathematical form of a simple harmonic oscillator. Consequently, we can represent the position of the pendulum over time using a cosine function, where the angle equals the maximum angle times the cosine of the quantity angular frequency times time plus a phase constant. From our simplified equation of motion, we can identify the key timing characteristics of the simple pendulum. The angular frequency, represented by omega, is equal to the square root of the quantity gravity divided by the length, L. The period of motion, which is the time it takes for one complete swing back and forth, is defined as 2 pi divided by the angular frequency. This simplifies to 2 pi times the square root of the length L divided by gravity. A very important takeaway here is that the period depends only on the length of the string and the local acceleration of gravity. It does not depend on the mass of the bob or the width of the swing, provided the angle remains small. Let us look at a practical example. Suppose we want to find the exact length required for a pendulum to have a period of exactly 1 second. To solve this, we rearrange our period formula to solve for the length, L. The length equals the period squared times gravity, all divided by 4 times pi squared. If we plug in 1 second for the period and 9.80 meters per second squared for gravity, we find that the required length is approximately 0.248 meters. This is just under 1/4 meter long. This calculation shows how pendulums can be used to define units of measure or to precisely calculate the local strength of gravity in a specific area. Now we move to the physical pendulum. Unlike the simple version, a physical pendulum is a rigid object of any shape that is pivoted at a point, O. This pivot is located at a distance d from the object's center of mass, labeled cm. When this object is displaced, gravity acts on the center of mass to create a restoring torque. The magnitude of this torque is negative mass times gravity times the distance d times the sine of the angle theta. By using the rotational version of Newton's second law, which states that the sum of torques equals the moment of inertia times angular acceleration, we can set up a new differential equation to describe how this solid object will swing. Just as we did before, we apply the small angle approximation so that the sine of theta becomes roughly equal to theta. This gives us an equation where the second derivative of the angle equals negative mass times gravity times distance d divided by the moment of inertia, all multiplied by the angle theta. From this, we find that the angular frequency is the square root of the quantity mass times gravity times distance d divided by the moment of inertia, I. The period is then 2 pi times the square root of the moment of inertia divided by the quantity mass times gravity times distance. This relationship is very useful because it allows us to measure the moment of inertia of complex shapes just by timing their swings. Consider a uniform rod of mass m and length L swinging from one of its ends. For a rod pivoted at the end, the moment of inertia is 1/3 times the mass times the length squared. The center of mass is located at the midpoint, so the distance d from the pivot is half the length, or L divided by 2. When we plug these values into our physical pendulum period formula, the mass, m, cancels out. After simplifying the expression under the square root, we find that the period of a swinging rod is 2 pi times the square root of the quantity, 2 times the length, divided by 3 times gravity. This shows that even for solid objects, the period is determined by the distribution of mass and gravity. The third type is the torsional pendulum. Here, a rigid object is suspended by a thin wire. When the object is twisted, the wire is deformed and exerts a restoring torque that tries to untwist it. This torque is equal to negative kappa times the angle theta, where kappa is the torsion constant of the wire. Using the rotational second law, we find that the second derivative of the angle equals negative kappa divided by the moment of inertia times theta. The period for this system is 2 pi times the square root of the moment of inertia divided by the torsion constant. A unique feature of the torsional pendulum is that it follows simple harmonic motion for large angles, as long as the wire is not twisted so hard that it permanently deforms. To summarize our findings, we have seen that pendulums are excellent examples of periodic systems. For a simple pendulum at small angles, the motion is simple harmonic, with a period determined by the square root of length over gravity. A physical pendulum accounts for the shape and mass distribution of a real object, with its period depending on the moment of inertia and the distance to the center of mass. Torsional pendulums rely on the twisting of a wire and do not require small angles to stay harmonic. These systems are not just theoretical. They are essential for accurate timekeeping and for conducting geophysical surveys by measuring variations in local gravity. To conclude, let us reflect on a few questions. First, think about why the small angle approximation is a strict requirement for modeling a standard pendulum as a simple harmonic oscillator. What happens to the math if the angle is large? Second, consider a practical scenario. If you have a grandfather clock that is running slow, meaning its period is too long, should you move the pendulum bob upward or downward to fix it? Use the period formula for a simple pendulum to justify your answer. Hint: think about how changing the length L affects the time, t. These concepts help bridge the gap between abstract physics equations and the machines we use every day.